Hello guys, today in this video we are going to discuss about ideal PN junction current or the ideal diode equation. So if you remember in the previous video we discussed about the minority carrier distribution. So I told you how these excess minority carriers, okay, from the N region to the P region, or my minor carrier holes from the P region to the N region, right? They diffuse and then they decay gradually as a exponential decay function. So that we have derived. You can revisit to that video where we actually determine the values of delta Pn as a function of x, or delta Np as a function of x. So Pn, that means excess magnetic carrier holes in the N region, and Np, delta Np means excess magnetic carrier electrons in the P region, that we have already derived. Now today in this video, using that excess magnetic carrier concentration function, we will be able to find out the ideal diode equation or ideal PN junction current, right? So the total PN junction current, when we are going to determine, will be the minority carrier hole diffusion current at x is equal to xn. The same diagram that I will show you, we have been doing it. So this is the space charge width I showed you, where we consider this to be xn plus xn, and this is minus xp. It's the metallurgical junction x equals to 0, right? So the magnetic carrier, I mean, suppose if I will write this is P region, this is N region, and then the holes, I mean, the majority carrier holes will diffuse from P to N region, and here at this point they will be treated as the, you know, as maximum at x equals to xn, and will be treated as the excess minority carriers. So that will lead to a value of diffusion current. So let us write it as Jp, J for current density, P for hole, and Xn because of the abrupt boundary. The same way, suppose this is the value over here for the electrons, majority charge carrier electrons will diffuse from N region to P region, and here you will get the maximum value of, you know, current, okay, current density at x, x is minus xp, right? So this is the whole thing. So if you want to find out the total PN junction current, that will be the, you know, because of magnetic carrier hole diffusion current at x equals to xn plus the magnetic carrier electron diffusion current at x equals to minus xp. So we will add this Jn at x is minus xp and Jp at x is xn, right? Okay. So how we will go about this? Let us first find out the minority carrier hole diffusion current density at x equals to xn. So let me just write this Jp, that is current density due to holes at x is equal to xn. We can write it as it is diffusion current. Okay. So the here the holes are injected, holes are diffused from P region to the N region, and at x equals to xn we are going to determine this value. So we can write this as E, okay, the minus E, the charge, okay, and then dP, the diffusion coefficient of hole, and then as we said diffusion, so the gradient dPn as function of x, okay, over dx, one dimensional we considered here. That's why I have written as ordinary differentiation. You can see that, right? So this is what we are going to find out, dPn by dx at x equals to xn, right? And then let me just tell you what is Pnx. We have already derived this in the boundary conditions. You can check the videos. Pn0, that is the thermal equilibrium hole concentration in the N region, plus the excess magnetic carrier, okay, due to the external excitation or external field, okay, whatever external excitation you give, that will lead to the excess magnetic carrier concentration which will be generated or created, right? So the thermal equilibrium carrier concentration here, this Pn0 value, this is constant, right? So we can write Jp at x is equal to xn as minus E dP. Okay, now if you'll substitute this Pnx as Pn0 plus delta Pnx, and this Pn0 That's the thermal equilibrium carrier concentration, which is constant. We will only remain with what? D by dx of delta Pn, okay, function of x, right? Ordinary x is equal to xn. So this is basically we need to determine. So I told you that we have already derived the expression for delta Pnx as a function of x, right? The exponential decay term in the minority carrier distribution in the PN junction, you can see that, okay? So now what we're going to do is simply substitute the value of delta Pn that we have determined and find the derivative and resubstitute it over here, okay? So this way we have already derived. Let me just write this as delta Pn x, the excess magnetic carrier holes here can be written as Pn function of x minus Pn0. So if I'll subtract this thermal equilibrium concentration from the non-equilibrium concentration when the external field is applied or external excitation is given, then the difference will give us the excess carrier that is generated in the process, right? So here we determine the value to be this Pn0 and then e to the power, I'm writing it in the bracket, but it is e to the power EVA by KT, okay, minus 1. Okay, e to the power EVA by KT minus 1, okay, and then e to the power again exponential of xn minus x divided by LP. This is e to the power, okay, read that way. Fine. So this is what we have obtained, okay. In the previous video you can revisit. Then we can write d by dx, which we need to substitute delta Pn function of x is equal to, take this Pn0, whatever the constant terms, exponential of EVA by KT minus 1. And then here you can see the function x, right? So we will take the derivative of that. So e to the power xn minus x as it is, xn minus x divided by LP, and then the derivative of this minus x by LP, that gives us minus 1 by LP. So this is the derivative that we got. Then we need to determine at x is equal to xn. So let us substitute x is equal to xn in this equation. So we can write d by dx of delta Pnx at x equals to xn, okay, will be now Pn0. The bracketed term is constant, keep it as it is, EVA by KT, right, minus 1. And then we have this xn, x is equal to xn. So you can see e to the power 0, that gives you 1. So we remain with minus 1 by LP, right? So write that. So finally we can write the diffusion current density at x is equal to xn as minus E, the charge, dP, the diffusion coefficient, and then this value that we determined for d by dx of delta Pnx is given by Pn0 exponential of EVA by KT minus 1 and then minus 1 by LP multiplied. Okay, so this is what we got. Okay, let us just rewrite in a better way. So we can Jp at x is equal to xn can be written as EdP Pn0 divided by LP. Okay, the same terms, I just wrote it in this way, exponential of EVA by KT, e to the power EVA by KT minus 1. Okay, in the bracket, right? The same way you can write what is delta npx, okay, and then you find the derivative of delta npx and you multiply with edn to that, then you can write what is the value of the current density, okay, the electron diffusion current density at x equals to minus xp, the other abrupt boundary, that is the abrupt boundary for the P region, right? So I'm just not doing it again. The same way we can write similarly Jn, Cp is replaced with N, and here we have the abrupt boundary is minus Xp, can be written as E, okay, and then same way Dn, Pn0 divided by, sorry, I mean Ln, here we need to write it as Np0, just like, you know, you got Pn0 here, it is Np0, Ln in the bracket, it will be the same function, exponential of EVA by KT. You can do it by your own, just to verify this, -1. Okay, so this is what we got. Now, if you want to find out the total current density in the PN junction, let us just add those. Okay, because you got, this is positive, this is also positive. So I will write the current density, total current density in the PN junction is now given by Jp at x equals to xn plus Jn at x equals to minus xp, right? And add them and just write it. So I will write E, you can see X, the bracketed term here, the square bracketed term, exponential EVA by KT minus 1 is common in both the expressions, you can see. So we can take that common. So we can write EdP Pn0 divided by Lp, that's there in the first expression. The second expression we got this, so plus EdN Np0 divided by Ln, so this will be added, and the common term that we have is exponential of EVA by KT minus 1, right? So this is the common term, right? So further, just to simplify it, we can write Ja, the current density, total current density is given by Js. Okay, Js I wrote for this bracketed term where we added these two terms. So Js for this whole thing, whole first bracketed square bracketed term, right, multiplied with exponential of EVA by KT minus 1, right? Where Js is given by this whole bracketed term, just highlighting it, this is Js, right? And this Js is known as the reverse saturation current density. So we call it as reverse saturation current density. Okay, and this equation, the equation that we derived here, that is given by J is equal to Js exponential EVA by KT minus 1. This equation is known as the ideal diode equation, right? So this equation actually relates the current and voltage in a PN junction, right? So these are the three things you need to remember. Js is reverse saturation current density given by this bracketed term EdPPn0 by Lp plus EdN Np0 by Ln. The equation that we found is known as the ideal diode equation, right? And this equation actually relates or gives the current voltage relationship in a PN junction, right? So now if you plot a graph, okay, from this particular equation that we got, okay, so we derived the relation J is equal to Js exponential of EVA by KT minus 1, right? Now you plot this, okay, for current and the voltage. So if you will plot a graph for this, that will give you, like, for positive values of VA, right? And here it starts with 0, so it goes like this for the, you know, like this, right? And similarly here for the reverse bias, okay, when you go in this direction, your current density, okay, varies like this, okay. And this value here you got is the saturation, reverse saturation current density. This is what we mean here. Okay, the JS value over here is given by the reverse saturation current density. This is because, okay, here the current density saturates for a particular negative, here you can see, right? So negative value of voltage you can see here somewhere. Okay, it starts saturating, right? So that's why we call it call it as the reverse saturation current density, right? So the overall the distribution is actually given by what? Let me redraw it. So this is your x equals to 0, the metallurgical junction, right? And then we have x is equal to plus xn, the abrupt boundary in the n region, right? In the p region, similarly, the abrupt boundary is x equals to minus xp here, right? Okay, so the we got the current density is maximum here. We wrote it as jp xn. So the value here through the junction, we can assume this to be constant like this, right? So we can assume to be constant. Similarly, we have the current density, the maximum current density to diffusion here minus xp. We can consider this value. So the total we can add those. Then what happens after x equals to xn as the minority carrier concentration decreases, right? Exponentially decays out. So we can draw the same current density. You can see, because here you will see that the whole diffusion current density will die out like the same way. As the concentration decreases, the diffusion current will also decrease or decay. Okay, so this is your whole diffusion current, the distribution I showed you here. Okay, the same way here also it will decay exponentially. We said it will exponentially decay. Why this happens? Because we said d by dx of delta pnx, or this factor will actually determine the diffusion, right? So when this delta pnx dies out exponentially, then the whole diffusion current density will also die out. The same thing happens here, d by d in the p region, d by dx of delta npx you take, right? So now this is the excess carrier that is generated due to the external excitation, right? Now the moment this is dead, I mean this decayed out, this factor delta npx decays out. Okay, then the current will also will gradually decay. So this is your electron diffusion. This graph, this curve actually shows you the electron diffusion over x, right? Over the distance. Okay, the same way you can, if you want, this is the minority carrier we discussed. Similarly, the majority charge carrier, if you want to show how it varies, then we can take the total current density. Suppose somewhere here the total current density, right, which gives you Jn at minus xp and jp at plus xn, and then add those, right? So same way you can see, like the majority charge carriers will decay, like the same way exponentially, so that every time you can just you can show what is the maximum value, and then will also decay out like this. So this gives you the majority carrier electron current, electron current, and here this distribution gives you the majority carrier whole current, carrier whole current. Okay, so this gives you the current distribution in a PN junction diode, the ideal current in a PN junction, or we can say what is the diode equation and the relationship between the voltage and current in a PN junction. Okay, thank you.